Hello everyone. In this video, I am going to discuss this response of undamped signal degree of freedom system to rectangular pulse force. The problem that we'll be discussing has been shown here. So at first, we'll consider SDOF system, which will be excited through a force of PT. The PT force will be varied through time, and it will be a rectangular pulse force which have a duration of TD. The maximum value of force, which is P naught, will be equal to 10,000 kilonewton, and the TD will be varied in different stages of the analysis. Then the problem considered has a weight of 615 kilonewton, and the column section will be of 1.5 meter rectangular, 1.5 meter square. The height of the column will be 3 meter, and the column material will be of 4000 psi concrete. So now I will jump to the SAP2000 software to draw the model. I will create a new model. I'll choose the units to be kilonewton meter and grid only. In the x-axis I will assign 2 grids, and in the yz axis also will assign 2 grids. The direction in the x-axis and y-axis doesn't matter. In the z direction, the distance will be 3 meter, which is the height of the column. Next we'll define the material. The material we are considering is of 4000 psi. So this material is already available in the SAP2000 software by default. So I'll just choose that. Then I'll choose the section. I'll create a new section which will be of concrete and rectangular. The dimensions will be 1.5 and 1.5. I will name the column to be the material will be of 4000 psi. Then I'll draw the column. Now, as the column has been drawn, I will assign a fixed support at the base of the column. Now, we will do a model time history analysis for the dynamic analysis, and for that the model analysis has to be said what mass it will be taking for the analysis. Now, as we have said that it will be a single degree of freedom structure, so the mass will be lumped at the roof. So we have to discard the mass of the column. So what I will do is that I will create a load pattern which will have the mass equal to 615 kilonewton, and then we will tell the system that the mass source that we have to consider for the model analysis will come only from the specified load pattern. So I'll go to define. I'll create a load pattern which will be named as SDOF mass. It will be a live load. Okay, and I'll assign the load to the top of the roof. As the load is being applied, now we will define the mass source. We will create a new mass source, and I will name it as the same as SDOF mass. Notice that it will not take the element self mass. It will only take the specified load patterns, which is the SDOF mass. I will change the default mass source to be SDOF mass. Okay, the mass source has been defined. Now we will check the model case whether it is taking this mass source which it's supposed to take. Yeah, you can see that it is taking the mass source from SDOF mass. So we'll go back. Now what I will do is that I will do a static analysis. So for that I have to assign a load equal to the 10,000 kilonewton, which we are supposed to provide here, the P naught value. Okay, so next we'll go to load pattern. I will define another load pattern which is named as the lateral load static. So I will assign this static load to the joint in the x direction, which will be equal to 10,000 kilonewton. Okay, so now we'll run the analysis. I will delete this value. I will name it as case 1. So now we will actually note two things. First of all, we will see what is the displacement that has been occurring due to the static load. So that is found from the deformed shape lateral load static. The value will be equal to 0.0101, which we have noted in this calculation. So you can see that we have noted the static deformation will be equal to 0.0101. So as we already note the load, so we can calculate the stiffness, which is the K value, and we found it to be 990099 kN per meter. Now as we already know the stiffness, using this simple equation of simple harmonic motion for finding the time period, we can find the natural time period of the structure to be 0.05 second. We will also check in the software whether this time period matches. We can do that from the model shapes. So see, from the deformed shape of model, we can find that the mode 1 has the time period of 0.05 second approximately. Okay, so in this way we have already found that the up to now all the things are okay. So now I will jump to some theoretical analysis. So this is the reference has been taken from the Dynamics of Structure book by Anil K. Chopra. So he has shown through Duhamel's integral analysis that the force vibration, when we are applying actually a rectangular pulse force during the force vibration phase, that means during the time when we are applying the force, the response has been shown to be in this way. And after that, when we stop the force, after that there is no force working on it, but due to the effect of the previous force, there exists a free vibration phase. So the response during the free vibration phase, which is the t greater than td, this equation provides the response of the SDOF system. And what he did is that he used these two formulas to plot the graphs that has been shown in the right. So actually what this graph does is that it shows different steps in different stages of TD values. So we are actually varying the TD. What TD means? TD means is that the duration of the rectangular pulse. Okay. So what he did is that, so in this first graph he used the TD values such that TD by Tn is equal to 1 by 8, and he found this graph. So in this graph you will see that in every graph of like this, we are actually plotting the ut divided by USD naught values in the y-axis. So it means the magnification factor, displacement magnification factor, and in the x-axis we are plotting t by Tn. So different time instances divided by natural time period of the structure. So that's how he has built these graphs. So what we find is that these graphs are actually from the analytical response. So what we'll do now is that we will do this analysis in the numerical simulation software, this SAP2000, and we will see whether the analytical solution matches with the numerical solutions. So at first I will unlock the model. Then I will define a function first. So it will be a user defined function. I will name it as pulse. Okay, so during the time period 0 there will be no value, so it will be defined as 0. Next we have to it is also that the at time instance 0 the value will also reach to p naught, but the SAP2000 software doesn't allow me to put two values of two same values of x for two different values of y. So what we'll do is that we will actually increase some, we will provide a small inserts of x, and we'll name the value to be 1. Sorry, okay. Next what we'll do is that I will provide the TD value. So in the first case what we'll do, I will consider the TD to be such that TD by Tn is equal to half. So the graph will be like this. So we have to see whether the graph actually comes out from the software in this way. So if TD by Tn is equal to half, we have to provide TD equal to 0.025. So that's what we'll be providing here, 0.025, and the value will be still equal to 1. I will add, and next what I'll do is that I have to provide the same value of x for y value of 0, but actually I cannot do that. The software doesn't allow me to do that, so I will increase it by a little amount and I'll turn the value to be 0, and then I will provide a long value, so maybe 0.5. I think 0.5 is too much, so I'll just reduce it to be say 0.25. Okay, so notice that I haven't actually provided the value of p naught, so I actually have to provide that. So I will do that using a scale factor. So first what I will do is that I will assign a load, I will define a load pattern for the dynamic load. So I'll name it that lateral load dynamic. So I will again assign a load pattern, assign a load to this joint under the lateral load dynamic, but I will provide a scale factor of 1. So here also I am providing the value of the force to be 1, so still the force is 1. Then I will do the trick. Then I'll go to the load cases that is already generated from this load pattern. Okay, so I will do what is that I will actually provide a time history function. So this time history function will be using the pulse force. The lateral load dynamic has been used, but it will be scaled to 10,000 value. Then I will set the output time step type to be 0.0001, then maybe 1000. So I'm just actually taking a lot of steps so that I can find a whole lot of values. Okay, So the time history analysis type will be linear. The solution type will be model, as I've already said, and we'll not use any damping, so I will turn it off. So no damping has been set, and other things are okay, I think. Yeah, they're okay. Okay, so this lateral load dynamic has been set to be a linear model history case. Okay, so now we'll run the analysis. So the analysis has been completed. I will go back to the slide and see that we are supposed to get a maximum analytical displacement, which I'll be getting from this graph, which will be equal to 2 into the static displacement, sorry, 2 into static displacement. So as we had already found that the static displacement is equal to 0.0101, so we are supposed to get a maximum analytical displacement of 0.0202 meter from this graph. See, um, see, this value is the maximum value and it corresponds to the ut by ust value of 2. So we are supposed to get this value from the structure also. Then again, if we see the t by tn value, the instant at which the maximum response has been found is at the t by tn value of 0.5. So we are also supposed to get at that value the maximum value. So we are supposed to get a maximum value at the time instance of 0.025 second. So now we'll check the software whether we are actually getting it and also whether the curve actually matches like this. So we'll note the top joint level, sorry, that is labeled as 2. So now we'll go to display, show plot functions, and the load case is lateral load dynamic. We'll define a new plot functions, joint displacement. We'll provide the joint ID to be 2, and we are concerned about the displacement in the x direction. So okay, for the betterment I will just change the name of the plot function. Then in the vertical function I will choose the joint displacement, and in the horizontal function I will provide time. Now I will display the function. So you can see that actually this kind of graph is being generated. So let's see whether it actually matches our graph. So see that we are supposed to get the maximum value of 0.0202 and at the time instance of 0.025 second. So we'll now observe the graph that the maximum value is found to be 20 into 10 inverse 3 or 2.026 into 10 inverse 2, which is equal to actually 0.0202. So we are getting the maximum value of 0.0202. But are we getting the value of at that time instance? So we are also getting that value where we are getting this maximum value, which is equal to 2.51 into 10 inverse 2 second, which is approximately equal to 0.025 second. So we can say that our analysis is okay. Yeah, so the curve also shapes like this. Now we'll check for the other values of TD, whether the graphs that has been shown by the Anil K, Chopra, which has been derived by analytical process, actually matches the numerical simulation. So in the next case, I will choose the TD value to be 0.05 second. So what we'll do is that I will save the file in a different name. I will name it to be case 2. And what I will do is that I will just change the TD value. So inside the time history function, the time data, the time duration, I will change that. So Instead of 0.025, this time we'll be using 0.05. And limit to be 0.051. So now it's like this. Then we'll run the analysis. So this time we are supposed to get the same values at the same time instance, but the curve will be different. Previously we are getting the maximum value at TDD by T by Tn at 0.05. Now also we are getting the value at 0.05. So everything is same, just the curve will be different. The curve will actually diminish after it reaches one cycle. So we'll check the software now whether it actually happens or not. We can see that it actually occurs, even though there are some differences in like this. So we can actually overcome that by so these are some actually rounding errors. So the time period that we are found getting here is equal to 0.05007, but we consider to be 0.05 second, and provided the uh, duration of the pulse like that. Also, while providing the duration of the pulse, we have provided after some instant, so there is also some loss in that case. So for those these small errors, there are error here, but if I see the whole value, I think we have to change the number of steps for that. So let's see if I can do that. uh, so I think if I change the number of output time steps to from 1000 to 10,000, okay, no, let's not change that one. Let's change the function. Actually, we'll provide a bigger function. So instead of 0.25, I'll provide 0.5. Sorry. So let's check now what happens. I think in this case I will get a bigger picture. No, I think I have to change the output time step also. So from 1000 I'll go to 10,000. So I think it will take a lot of time to run. If not, the results, I don't know. Let's see. Yeah, it's taking a lot of time than before. Okay, let's go. So the analysis is done. Now let's check the results. Yeah, so you can see that even though there are some small deflections here, it was supposed to be straight line like this. Yeah, so we can say that it's quite okay, and the maximum value is the same as before, the 2.0202 value at the 0.025 seconds. So the case 2 is also justified like this. Next we'll check the case 3. So in this case what will happen is that we will provide the TD by Tn value of 1.75. So TD value will be equal to 0.0257 0.0875 seconds, sorry, and the generated output graph will have two different levels of sine curves. So the first sine curve will have the maximum value of 2 USD, but when it actually goes after the t by tn equal to 2, at that time the maximum response value will decrease. So we'll check whether this pattern follows in the numerical simulation also. So I will again save another model named as case 3. So this time td by tn will be equal to 1.75. So td value we are supposed to provide it as 0.085 second. So I'll change it like this, 0.08575, sorry, and also this one 0.0876, because we already said that it doesn't actually take the same value, that's why. Okay, now we'll run the analysis. So this time here also we are supposed to get the same maximum analytical displacement value at the same maximum instant, but there will be two loops this time with the maximum value, and other loops will be of a less value. So we'll check whether this happens or not. So see, for the betterment I will just scale it down a bit, so I'll see up to 0.0 to 0.2 maybe. Let's change it to 0.2 maximum value. So yeah, so the curve is like this. So see, it is quite similar to what we are supposed to get from the analytical analysis. So see that the maximum value is supposed to be at 0.0202, 0.0202, and at the instant of 0.025 second. So we are getting the same value here also, just like the previous analysis. And also see that the next peaks, the two peaks, see with that here also we are getting two peaks before it actually diminishes. So after that we are getting the peaks which have a lower value. So here also we can find it. So I think our graph is justified. So next we'll see another case. No, okay, so this is the last case. So it can be said that the analytical procedure, the analytical response function that has been developed by Mr. Anil K Chopra, which we can actually simulate the same response also in the SAP2000 by the process that we have discussed. So thank you for today.